Please take it away.
Thanks, Marcia. Thanks to the organizers, and thanks to all of you for staying here, the very last talk before the very last lunch of this workshop. Today, I'd like to tell you a little bit of a story about gravity, classical gravity, in the presence of finite boundaries. This is work that we've been doing in the last couple of years with a great group of people, from which I will highlight Raul, that gave kind of part one of this talk on Wednesday, and I'm sure you all remember it. And then Chawakorn Manerat, who really is the guy that has been pushing the boundaries of this project. All right, so I thought of starting with some introduction of why boundaries, but then I realized that we are in a holography workshop, so we all know the importance of the time-like conformal boundary of ADS in holography. And so, as it already appeared in Raul's talk, we are already used to moving the boundary a little bit inwards when we do processes such as holographic renormalization, to tame some of the divergences that appear because of the infinite volume of ADS. And there are also different proposals on how to actually move that cutoff to a finite size in the context of ADS. I will not talk about much of that because Raul already covered that part during his talk, but I will try to address a little bit the other two cases. So when we have a positive cosmological constant, somehow we are more in need of these boundaries, or at least some kind of feature, if we want to describe the experience of some inertial observer, for instance, in a universe that is experimenting accelerated expansion. These observers are surrounded by cosmological horizons. The space is always finite in there, and somehow we need some anchor from which to describe gauge invariant observables in those finite regions of space. Those can be a proper observer, some field like the inflaton in inflation, maybe a black hole, or here we will consider the case of having a finite boundary inside the static patch of the sitter. Historically, boundaries appeared in trying to describe evaporating black holes in flat space. It appeared already many times in this workshop that the flat Schwarzschild black hole evaporates, and so its specific heat is negative. It's hard to understand thermodynamic systems with negative specific heat. So York had this idea in the 80s, where is here York, in the 80s, to take the Schwarzschild black hole and put it inside a finite box in which they specify Dirichlet boundary conditions. So this is my representation of the Euclidean Schwarzschild black hole. This is my box. We put it in there, we cut the space. I will be more specific later. But that calculation created, at least with a given temperature and a given area, two black holes, one of which is a large black hole that had a positive specific heat. So boundaries appeared as a way of stabilizing these thermal objects. Of course, we can try to think to do the same with a piece of the sitter, and then we can try to cut the sphere, that is the Euclidean static patch, and put again a Dirichlet boundary. So we take our sphere, we put it in the box, and that exercise has been considered already long time ago as well. This is the Lorentzian representation of that. And the result of that calculation, no matter how you choose to cut the static patch, is that the specific heat that you will get for the sitter will still be negative. So maybe these boundaries are not that helpful in trying to understand the static patch. There's another box that we all know and like, that is putting our black hole inside anti-de Sitter. And of course, we know the result of that experiment. Now we put the black hole inside ADS. There's a large ADS black hole. We compute the specific heat. And now we not only get positive specific heat, but we also get the result that you get from a CFT at finite temperature in one less dimension. Okay? We can try to do the same in the static patch of the sitter. So in this case, we will try to embed some part of the static patch inside ADS. And again, this is not new and has been considered some 20 years ago now by Veronica Mukund and collaborators. And what they found in that paper is that there was some obstruction. So these are the type of Penrose diagrams that they were getting. This is the ADS boundary. There's a black hole horizon. And then all the DS bubbles were hiding inside the event horizon. So the problem at least was as hard as describing the interior of black holes in holography. Well, some details. This obstruction came from requiring that the matter had to satisfy the null energy condition. And there are some way out of this. If you consider two-dimensional spacetimes, you can embed a little piece of the sitter into an ADS space in 2 dimensions or near 2 dimensions and create some geometries that we call centaur geometries, and we've been discussing this in this workshop, but that's not what I would like to talk about. Here I would like to stay in higher dimensions and try to tell you about some new developments that has been going on in the mathematical community or mathematical relativity regarding spacetimes with finite boundaries, and try to apply those into this context and see if they can help us with this problem. Okay? So the short outline of this talk, I will start with some flash summary of the status of the boundary problem in general relativity, and this is just flash because I assume you remember at least a little bit from what Raul told you or told us on Wednesday. And then I will try to tell you about 2 different applications. The first one related to this story about thermodynamics of the static patch. And the second one related to trying to apply holography and trying to get at least, well, a little bit more microscopically into what these boundaries are doing in a plausible dual theory. Okay? So let's get into it. So this is the boundary or initial boundary value problem in GR. We will consider some manifold that has a finite boundary. The problem will be divided into Lorentzian and Euclidean. So you already see we have 3 signs of the cosmological constant. This can be Lorentzian or Euclidean. We can consider the inside or the outside solution of this tube. So very soon you start getting lots of different cases. But I will try to keep as generic as I can and just specialize at the very end. So I will try to focus on generic details of this problem. So we are looking for solutions to general relativity. In principle, for these boundary value problems, I will consider higher dimensional gravity. I want dynamical gravity in the bulk. These different boundary conditions can also be considered in lower dimensions, of course. I will not consider matter, and again, this can be done with or without the cosmological constant. The question basically is, what are the allowed boundary conditions on gamma? So let me try to describe these both pictures over here. So this is a Lorentzian manifold. There's an initial Cauchy slice that I'm calling sigma. And then there's gamma, my time-like boundary. And I want to fill this tube with a solution to general relativity that will have some initial conditions and some boundary conditions that I will need to specify on gamma. Of course, in the Euclidean problem, there's no initial slice, and I just specify boundary conditions on gamma and try to fill my spacetime with some solution to GR that is smooth in the interior. Okay? Okay, and what happens, as Raul was telling us, is that the initial boundary problem, so now I'm sticking to the Lorentzian case, in general relativity, if you choose Dirichlet boundary conditions, generically is not well posed. This is a theorem by Ann and Anderson from a few years ago. And being not well posed means for us that there's lack of existence. So if you, well, let me tell you first what it means to do a Dirichlet problem. It will mean that at gamma, I will specify the induced metric for all times. and then I will try to find the solution in the interior. And so the first thing that these people proved is that generically, if you specify any induced metric on gamma, you will not be able to find a solution in the interior. And this is because generically you will not even be able to satisfy the Einstein constraint equation at the boundary, so you don't even need to think too much about the bulk. The generic GMN will not satisfy the constraint equation at the boundary. And this is a little bit worse because if you manage to find a solution, say that you have a full space-time, you select some slicing, you put that as a boundary condition, that of course will be a solution to my initial boundary value problem, but then the problem will be that that solution is not unique. So what will happen is that you will find an infinite family of solutions that locally they look like diffeomorphisms, but because of the presence of the boundary, they become physically distinguishable solutions, and then the problem is not unique anymore. Yeah.
Left part, it is just like solving Hamiltonian constant on a radial slice, that problem.
Yeah.
This is the existence problem.
Yeah, it's on a, yeah.
Okay.
Are there other questions? Okay. So given there were some questions during Raul's talk, let me make some comments about this problem. So the first one is that the initial value problem, as Raul was saying, is known to be well posed from more than 50, 60 years now. So if you specify initial data that consists on specifying the induced metric and the extrinsic curvature at a full Cauchy slice such that they satisfy the constraint equation at that slice, it is proven that there's a unique smooth development up to Cauchy horizons of that problem. And for some reason, the initial boundary value problem took another 50 or 60 years for mathematicians to consider. The not well posedness of this problem in gravity is different to what happens to other types of matter. So scalar, Maxwell, and Young-Mills are well posed. And again, this is a comment about generality. So particular kinds of Dirichlet data are well posed, are unique, and exist and are unique. And they are related to properties of the Brown-York stress tensor that allow to do some transformation between conformal boundary conditions and Dirichlet boundary conditions. And the proof of that has come very recently in another paper by Anna and Anderson that appeared this year. And in fact, these Dirichlet boundaries has been used for the Sitter holography in work by Eva Silverstein and Gonzalo Torroba and their collaborators, both in lower dimensions and very recently also for 4D. Okay, but today I would like to talk about this other set of boundary conditions that we call conformal boundary conditions. These were conjectured in this same paper by Anna and Anderson to be well posed, and I will tell you a little bit the story about how that is going since 2021. But basically what we do in this problem is first we set the same initial conditions on sigma as we were doing before and as we do in the initial value problem. But then on gamma, we will not fix the entire induced metric, but we will only fix the conformal class of it. So these square brackets over here are saying the conformal class. We fix the whole metric up to a conformal factor. And now we have an extra degree of freedom that we need to specify there, and we will exchange that for the trace of the extrinsic curvature at the boundary that from now onwards will be called K, the trace of KMN. And the claim is that that conformal data plus some data that we need to specify at the corner, at the intersection between sigma and gamma, will lead to a unique, well, will lead to the existence of solutions and the uniqueness. All right, so comments about this. So these boundary conditions first appeared in work by York in the 80s in trying to see what kind of data in some slice of space-time satisfies automatically the constraint. They didn't want to consider the case where you need to specify G and specify K and then satisfy the constraint. and they realized that these boundary conditions are better for that. They reappeared in our field in the context of fluid gravity, when people were considering what happens to gravity very close to event horizons of either black holes or cosmological horizons, and they realized that specifying Dirichlet data near the horizon was the wrong problem. There were obstructions to solving that problem to second order, and they needed to change the boundary conditions into something that looked like these conformal boundary conditions, of course without knowing about all these theorems that were not there. This problem is proven to be well posed in Euclidean signature. It's elliptic, and we know that for quite some years now, and Witten wrote some nice lecture notes that translated that 2008 paper into our language. And there are some very recent developments on whether this conjecture by Jan and Anderson is true or not. So they published a linearized proof about any Einstein background early on this year. But then there's the existence. So if you linearize the problem and you see what type of frequencies are allowed to exist at the linearized level, you will see that for spherical boundaries at large angular momentum, you will see frequencies that have a positive imaginary part. So this will make our boundaries to grow exponentially in time. And not only grow, but they will grow a lot, even though related to the real part, they will grow slower. They will still grow very fast with angular momentum. Yeah. This is in flat space, but this is quite generic because most of these proofs are about what happens in what people call the standard Minkowski problem, where they zoom a lot into that corner region, and the curvature of space is not very important.
And is there, yeah.
Of course, if you are very close to the ADS boundary, we know that that problem is well posed, and yeah.
But is there an intuition for this behavior?
Not yet. Yeah, it appears quite generically, but we still. I think an important problem in all this program is to understand why these boundaries want to have this growth. Yeah. And this growth was used by these people, Liu, Rial, Santos, and Weissman, to show that these boundary conditions do not satisfy what is called the Hadamard criterion. That means that bulk solutions should be continuous with initial data. So if you move a little bit your initial data, you will find a solution that will be close to your previous one.
Is the normal Dirichlet or Neumann problem well posed in Euclidean, or is this?
No, so in Euclidean signature, the Dirichlet-Neumann problem is not well posed.
Okay, so only conformal.
In general. Again, there's a similar thing, not with the Brown-York stress tensor, but if the trace of K has positive sign, then that problem is also well posed in Euclidean. So there are the statements between Euclidean and Lorentzian regarding well-posedness are very similar.
Thanks.
Are there other questions? Okay. So that's the status of the initial boundary value problem and the conformal boundary conditions. We can keep discussing whether that means that we should use them or not, but for the rest of the talk, I will assume that these boundary conditions might be useful and see what we get by applying them in the context that we usually like to use in holography. In particular, I will start by considering the Euclidean case of the sitter, and let's see how that goes. So another nice feature of these boundaries is that so a big problem, let's say, in the sitter holography is where's the holographic screen, or where the dual theory lives. If you are inside the static patch, there's no natural place, so you can think that the holographic theory lives very close to the observer, and that goes along some ideas regarding holography in the static patch that date from some time ago, and now they've been revisited in the context of algebraic QFT, the existence of the observer, and some things that we've discussed over this workshop. But there are also some ideas in which they try to put the boundary very close to the horizon. The horizon is a null surface, so we regulate that by putting a stretched horizon, a time-like surface very close to that horizon. And some people like to consider holography by putting a putative boundary over there. Of course, we don't have yet any complete model of this, so these are just proposals. But these boundaries allow one to move from one to the other and see maybe how to connect the two ideas. So this is the Penrose diagram of the Sitter space. This is one static patch. And then if you put a time-like boundary at a constant R surface, this will distinguish two different regions. There's one that does not contain the horizon that we will call a pole patch. And there's a second one that is the region between the boundary and the cosmological horizon. And that one we will call the cosmic patch. Okay, now we will go to the sphere, and those will be different patches of the sphere. And we will play the same game that Gibbons and Hawking were playing back in the day. We will define, in the standard Dirichlet problem, we define the canonical partition function in the saddle point limit by computing the on-shell action for these saddles. And this partition function is a function of your boundary data, that in the case of Dirichlet is just beta, the size of your thermal circle at the boundary, and this R, that is the size of your spatial sphere at the boundary. I will restrict myself here to spherically symmetric configurations, and moreover, they will be static. With conformal boundary conditions, beta and R by themselves are not well defined because the conformal factor of the metric at the boundary is not defined, so I can change the size of these two things, but the ratio between them is well defined, and so this new conformal canonical partition function will depend on something that I will call beta tilde, that is an inverse conformal temperature, beta over R. And then the other parameter that will control this quantity is K, the trace of the extrinsic curvature at the boundary. Okay? And this game I can play for any value of the cosmological constant. Here I'm restricting myself to the Sitter just because I have only 20-something minutes left. But we can do that. Okay, so if we want to impose these boundary conditions, we need to be a bit careful on on what is our Euclidean action that we will put on shell. If we want this action to be stationary under conformal boundary conditions, we cannot put the usual Gibbons-Hawking-York term. That will give a Dirichlet problem. Instead, we need to change the boundary with this coefficient over here. There's this 1 over d minus 1 that makes the action stationary under conformal boundary conditions. One can think that given that these conformal boundary conditions only change the coefficient of this term, this is just root g or h times k, one can consider the case of an action where you put some arbitrary condition over here, and one can try to guess what are the boundary conditions that induces, and that was done by Liu, Santos, and Weisman. The type of boundary conditions are also of the conformal type, so they will keep the conformal class fixed, but then they will not fix k, but k times some power of the determinant of the induced metric at the boundary. So that's a one parameter family generalization of this that will go in some particular case to our conformal boundary conditions result. Okay, once we have our Euclidean action, we can take saddles of this and compute all the thermodynamic quantities that we want. Now, instead of keeping the area or the volume fixed, we will keep K fixed to take our temperature derivatives, and we can find a conformal energy, a conformal entropy, and a conformal specific heat. All right? Let's do that exercise for the Sitter in the case where we are in 3 space-time dimensions, bulk space-time dimensions. If you do that with Dirichlet, you will always find a negative specific heat. Now you do that exercise with conformal boundary conditions, and you will get this very nice result. So CK is something like 2 pi squared, C conformal over 3 beta tilde. That first is positive, and second is the result of a 2D CFT at finite temperature with a central charge that has this form over here. So it's very similar to what you would say a Brown-Renault central charge, but it has some dependence on K. If we plot this result, this is what you get. So this green one is the de Sitter result. K goes from -infinity when the boundary is very close to the world line, the observer's world line, to +infinity when the boundary is very close to the stretch horizon. And we see that this function is a monotonically decreasing function from the world line to the horizon. And if you consider the same for the BTC black hole, you will see this yellow line over here that will go from infinity, that is when the boundary is very close to the black hole horizon, and it will come to the Brown-Renault value when KL is equal to 2. That is the asymptotic, the value of the extrinsic, the trace of the extrinsic curvature at the conformal boundary of ADS3. Okay? So this is the result. In both cases, you get, for any temperature, the conformal result with these central charges that depend on the value of KL. Now we can go to 4 dimensions. 4 dimensions is more complicated because you also have black hole solutions. And so the types of patches that you can consider now are like cosmic patches, pole patches, but you also have black hole patches. And so this is some kind of summary that I don't want you to look at of what happens for any given value of K and beta tilde. The only thing I want you to know about this plot is that this region over here that is light green, it's a region where you will have cosmic patches, so patches of the Sitter space that have a cosmological horizon, that have positive specific heat, and are thermally stable. Okay, so conformal boundary conditions in 4D allow you to define cavities that have a positive specific heat in 4 dimensions. And if you look what happens in the large temperature limit, you will find solutions that look very similar or analogous to the ones in 4 dimensions. You will get expressions now that go like 1 over beta tilde squared and have some non-trivial function of K that somehow can be interpreted as counting some kind of degrees of freedom in some maybe microscopic theory. In fact, you can also take the large K limit of this expression, and that will take you into the flat space regime of this solution, and you will find that the specific heat is positive, and now given by a very simple expression that is 1 over beta tilde square times G Newton times K squared. So for the flat black hole, you find not only a specific heat, but a conformal temperature, a conformal specific heat that defines for you some quantity that we are calling NDOF, that is somehow counting, it might be a way of counting microscopic degrees of freedom and taking a large N limit in a theory that without this boundary does not have any dimensionless parameter to take a large N of. So this K somehow is providing us this quantity. Are there questions? No. Okay. And in fact, this result has been analyzed by the group of Edgar Shagulian more systematically in a high temperature expansion, where they also consider the subleading terms in this expansion, and they try to study that in terms of effective thermal field theory. Okay, so that's kind of the end of my first application. So a bit of a summary. We are studying, or we found a new way of studying quasi-local observables in gravity with finite regions of space-time. This can be done for any value of the cosmological constant. And if you look at the thermodynamics of all these solutions, you will find some nice behavior that includes positive specific heat and some kind of conformal result at very high temperatures. Of course, all this is in the saddle point approximation, taking G Newton to 0. And one might ask how stable this saddle is, and for that you need to study the Lichtner-Lowitz operator, and that's what Liu, Santos, and Weissman did in a paper last year, and they found, at least for the flat black hole, they found one negative mode in this operator that they claim is associated to the boundary itself. So that's another, that might be related to the other instabilities that Roberto was asking about, but it's not completely clear what's the relation between these two types of instabilities. Okay, and so I'm done with 1 and 2. So I wanted to tell you a little bit about another application. So far we only consider static and spherically symmetric solutions. But given that now the conformal factor at the boundary is not fixed, we can also consider solutions that have some time dependence on this conformal factor. Okay? So let's start with a bulk solution that is has some spherical symmetry, is of this form. And let's consider boundary conditions of this type. So at the boundary, the metric will be this times some conformal factor that is not specified and can depend now on time. The trace of the extrinsic curvature, I will fix it to be constant and not time dependent, okay? And then what happens is that if you impose this k to be constant with this induced metric, you can go to Mathematica, ask BIF Geo what that gives, and that will give you a second order differential equation for this conformal factor if you assume that the conformal factor only depends on time. Okay, this is a highly nonlinear differential equation for any f of r and any dimension of space. And of course, it will be nice to find all the solutions to this equation. It will be second order. I will need to specify two pieces of initial data. One of them will be related to this corner data that I was talking about earlier. But this, at least this equation is in Euclidean signature where that corner is not there. And so quite remarkably, there are some cases in which analytic solutions can be found, and we can really classify all these different solutions with constant curvature. This is some work that Chawakorn is doing and hopefully will appear soon. But let me tell you about one of those cases that might relate to things that people have been discussing in this workshop. So let's go back for now to anti-de Sitter space in d dimensions. The conformal boundary of ADS has fixed trace of extrinsic curvature and is given by d minus 1 over L, independent of G0 and GD that are the boundary data that we usually specify in ADS. Whatever those two functions are, if you consider the limit where the boundary goes exactly to the conformal boundary, k is fixed to this value. And so you can try to see what happens if you put this value over here, then the conformal factor grows very large, so you can take some limit of this equation, where you just take k to be this plus some small deformation. Okay, so I'm almost at the conformal boundary of ADS. I bring it a little bit inwards, and I ask, what's the equation that determines the dynamics of this boundary mode? Okay, and what I get is this equation over here that I still don't know how to solve analytically and exactly and find all the solutions to this. But one can see that if I put here d equals to 3, so now if I restrict myself to 3 dimensions, you can maybe recognize that the equation of motion for this boundary mode is the one-dimensional Liouville equation. And that one we do know how to solve. So that's nice. I think that will be mostly explored in a paper by Edgar and his student that will come soon. But you can continue and try to ask yourself whether this equation of motion, this Liouville equation of motion, stems from some effective action for this boundary mode. And one can proceed in the same way as we do in deriving the Schwarzian action from the spherically symmetric sector of three-dimensional ADS gravity. And one does that exercise, and now you go to some effective theory in 2D where the boundary condition for the dilaton is not anymore that the dilaton is fixed at the boundary, because you are allowed to fluctuate this conformal factor, so there will be a little bit more involved boundary conditions in your 2D gravity theory. But when you do that exercise is still JT, the bulk term is still JT. You do that exercise of leaving these 2 degrees of freedom off shell, and you get an effective action that takes this form over here. So the first term is the usual Schwarzian derivative that appears in the standard JT story, but then this degree of freedom, omega, is not fixed anymore and has its own dynamics that are ruled by this action over here that is, again, a Schwarzian type action, but crucially has a minus sign over here compared to the standard Schwarzian action. Yes? Yes. In this exact limit where k, in this exact limit where k is just 2 plus delta k, it's not very important what's inside the ADS. It's just the ADS boundary what rules this. Okay, and I think this action is interesting because first it shows the role that is playing that this dynamical boundary is playing, and second because it might allow for some kind of quantization of this theory. This is the most microscopic we will get, I think, in the context of these conformal boundaries. And you can reinterpret this action as the standard Schwarzian action, but couple it to what people call one-dimensional quantum gravity. So in the standard story of the Schwarzian, we keep the size of the thermal circle fixed, and that gives the Schwarzian, but now we will consider the case where this circle is not fixed anymore and is allowed to vary. The consequence of doing that is finding this action that has another Schwarzian, but with a negative sign. And somehow, yeah, we found this action when we were looking at these centaur geometries in 2 dimensions for different reasons, and then Dio, Diego, and Statis analyzed this more closely in a different paper. So this, I think, because solving this equation is quite hard in full generality, this, I think, is the closest so far we will get to having a microscopic interpretation of these conformal boundaries that will happen when the boundary of this conformal boundary is very close to the conformal boundary of ADS in 3 dimensions. If you start looking for higher order corrections, that's something that I think it can be done. I don't know the answer. I cannot write the answer right now, but then you will need to start incorporating pieces from the bulk that will interact with this mode. So there will be some matter, some stress tensor interaction appearing in this effective action. Questions? Yeah.
To this theory, bulk matter.
Bulk matter or boundary matter?
Well, I mean, you're starting in ADS3, say that you put some matter in ADS3.
Yeah, well, I think yes.
That's going to induce some matter couplings at the boundary. Is it,
I think the answer is yes. I don't know exactly the details of that. I can tell you a few things afterwards. Yeah. Are there other questions?
You would think that if you go very close to the boundary of ADS, this action is just a Legendre transform, where you couple your CFT with a finite cutoff to a conformal scale factor, and then you make the conformal scale factor dynamical. If you do that in ADS3, you kind of get the Polyakov action with or without a cosmological constant, depending on whether you include a counter term. Is that not roughly what's going on in all these cases, or is it very? Do you do something conceptually very different?
No, I think it's something very similar to that. Yes. Yeah. Horacio? So TT bar is different. Yeah. So TT bar is claimed to be dual to ADS with a finite cutoff Dirichlet boundary. These deformations, I think they are different. So what the TT bar deformation usually does is to reorganize your density of states in some way, but they keep the entropy fixed. So the central charge of the theory, I think, doesn't change. And it's just some reorganization of your states inside inside those that are counted by that entropy. In here, I think the deformation is a little bit different in the sense that these C functions that we are getting change as you change K. So yeah, it would be nice to see what's the relation between the TT bar deformation and this type of effective actions, but they seem to be a little bit different. It's not, well, yeah. Yeah.
What is the symmetry of the action in this case?
I don't know. There are two SL2Rs here. Yeah. Okay. The funny thing is this minus sign that would be nice to interpret properly.
That was present in the center case as well, right? It was like a U1.
Yeah, that was present, but in the center case, you will get a plus over here that will break some of the SL2R symmetries over here to a U1. In here is still SL2R.
Oh, okay.
I don't know.
Similar pathologies appear when you change boundary conditions and then you induce gravity at the boundary.
But pathological in what sense, you mean?
Well, you get ghosts.
Yeah, I don't know. There are, yeah, this minus, yeah. I think all this is related to the same fact that you have these modes that like to grow in time. And yeah, it might be the same that appear in usually in Euclidean gravity. But I think in this particular case is the one where we will be able to make those statements very clear and understand what's going on, because just the effective action is very precise. But this is all work to be done. All right. Yeah, I'm basically done because Marcia is looking at me with a hungry face. There are way too many things to do, some of which you already asked about. But given maybe this is a quantum information conference, some of the most pressing ones is whether these boundaries exist beyond the classical limit. In quantum gravity, what is the microscopic dual of these gravitational observatories? And if the answer of all of this is that they exist and they have a microscopic dual, what is the quantum information of these theories? One can imagine of constructing something like Ryu-Takayanagi surfaces, as we have seen many times in this workshop. Now they will not have the usual divergence that you will get when you push the endpoints all the way to the boundary. So these entropies will not have the standard UV divergences that entanglement entropy in local QFT has, But maybe they can say something more about the nature of this theory, if there is a theory that lives on these conformal boundaries. So that's all I have to say. Thank you very much. I forgot, I have one more thing to say. I'm organizing a workshop on this by the end of the year in the Simon Center with a bunch of friends. So if you found this interesting, or if you found that this is complete nonsense, please come to this workshop and tell us why. Yeah, questions?
Okay, yeah, maybe a couple of questions before we go for lunch.
So in these cases that you describe with the sitter, you empirically find a conformal answer for the entropy.
Yeah.
But is there some other observable that would be conformal, like I don't know, 2-point functions anchored on the boundary or something like that?
Yeah, it would be nice. Yeah, this is on the to-do list. Probably, yeah, it would be nice to find some. Yeah, so for instance, one nice calculation is to try to do this Ryu-Takayanagi computation and see if the same central charge appears. Well, there will be no log. Yeah, I don't know. But the correlation functions are probably a good place to see whether this conformality holds or not. Yeah, we also computed for the ADS case, we computed the sphere partition function, and it's not exactly this central charge, the one that appears that you would expect. But yeah, I agree that some computation like correlation functions in this with these boundaries should give some better idea of what's going on.
More questions? Well, if not, let's thank Damian again.
Thank you.